Hello, I'm Andy Briggs, and welcome to the amazing Astronomical Alphabet, a weekly programme in which my Astro Radio co-presenter Daz and I will be talking about anything astronomy related which begins with the week's letter of the alphabet. We'll each choose some things to talk about which are in some way related to the universe, but neither of us will know what the other has chosen. We will then reveal facts about them which are weird, strange, bizarre, or simply interesting. Hello listeners, this is me, Andy. How are you, Daz?
I'm fine, thank you very much. No homework, so it's been relaxing. No long, tedious films to watch, but yes, it's absolutely...
I'm sure we'll find you some more homework at some point, Daz. So we're back with the amazing Astronomical Alphabet. We're going to tell you some interesting, bizarre, or just plainly strange things about objects in the universe, beginning with the letter C. I've chosen a few, Daz has chosen a few. We don't know what the others chosen. So we'll just crack straight on. And I believe, Daz, it's your turn to go first this week.
Oh, lovely jubbly. So I'll get in. It's probably a bit of an obvious one, but actually I was just thinking about it while you were just talking. I think, does this actually count as a C?
C is for what?
C is for, it is for Charles Messier.
Well, yeah, that's fine. Begins with C.
That's good. That's good. I didn't, because I suddenly thought, well, were we doing surnames or were we doing Christian names?
But no, Charles Messier is fine. Charles Messier is absolutely fine.
Right. For those who don't know, Charles Messier, he compiled a catalogue of nebulae and star clusters. Basically, he was a comet hunter, and he was always coming through across all these fuzzy objects that looked like comets, but they weren't. They're not moving, so he knew that they were static in the sky and they weren't what he was looking for.
Right.
So basically what he did is he started to basically make a note of their position, so that when he did his observations, if he come across these fuzzy patches, he knew what they were. They weren't what he was looking for.
Okay.
And he did actually discover 13 comets in his life. So he was quite successful at it. But just a little bit of background on him. I mean, I could sit here and I could just reel off all the Messier objects in the catalogue, but that would be just tedious.
Yes.
But so I thought what we'll do is we'll actually find out a bit about the chap himself.
Okay.
Now, there's going to probably be some mispronunciations because I'm no good on French names and place names and things like that. But just please bear with me. No need to write in nasty letters.
I'm sure our French listeners will forgive you, Daz.
Either that or they'll take out a contract. So he was born on June the 26th, 1730 at Badonviller, northeastern France. He was the 10th of 12 children. 6 of his brothers and sisters died. Yeah, I should have bought a telly. 6 of his brothers. All right, buy a good book. 6 of his brothers and sisters died at a very young age, which wasn't unusual in the 18th century.
Right. True.
But some sources say that the Messier family were poor. But in fact, his family was quite wealthy, but they fell on hard times when his father, Nicolas Messier, died when Charles was 11.
Oh, dear.
Yeah, exactly. So it meant basically he had to give up his education, so his formal education. But he was homeschooled by his older brother, Hyacinth.
Hyacinth?
Yeah, exactly. That's what I will spell it for you so you can make up your own. It's Hyacinthe.
Right.
Hyacinth.
As in hyacinth bouquet.
I presume, yes.
I've come across this before in French. It is hyacinth can be a man's or a woman's name, and if it's a man, it ends in an E, I think.
Yes, well, he was Charles's older brother, so he took on his schooling basically. Charles learnt the skills of an administrator from his brother over the course of 8 years, and it was these methodical skills that he had later applied to his systematic search for comets and his observation and recording of astronomical objects. So his brother did a pretty good job.
Wow.
He he had a passion for his passion for astronomy was sparked by when he observed the Great Comet of 1744 when he was 14. The comet, whose official designation, which really isn't relevant, but I'll give it to you, is C/1743 X1,
Right.
and which is also known as Comet de Chazux,
Right.
or Comet Klinkenberg. Klinkenberg.
Sorry, Klinkenberg?
Sorry, yeah, I do. Yeah, Klinkenberg was a spectacular comet reported to have 6 tails. Sorry, I just find that funny. I do apologize, Mr. Klinkenberg. At the age of 21, Charles was hired as a draftsman in the French Navy. He learned to use astronomical instruments and became a skilled observer. He was promoted to chief astronomer of the Marine Observatory in Paris, where he pursued his passion for comets.
Right.
So as I said, he discovered 13 comets in his lifetime, and it earned him the nickname from King Louis XV of France, the Ferreter of Comets. Sorry, the Ferret of Comets. So that was his nickname, yeah, Ferret of Comets.
Right. Now, I presume, I mean, I don't know about you, in my life, I can never remember a comet Messier. So I would assume I'll be talking, they must be long period comets then, because I can never remember any comet Messier in the sky.
I did have, I don't think I've put it away, I think, but I did actually have a list of the comets they have, but I think the names were added to them afterwards. They were just given designated numbers.
So they're not named after him then?
Yeah, I assume not. I'll have to look at the chart I had that listed his 13, because he's also co-discoverer of a 14th one as well. So he discovered for himself 13, and but altogether his name in a way is on 14 of them. So as I said, this great comet of 1744. I won't say the name again because I'll laugh again.
Mm-hmm.
It displayed
you
six
mean
tails.
Comet Klinkenberg?
Yeah, Klinkenberg. And it had 6 tails, which actually rose above the horizon, which I think that could be quite spectacular.
That's interesting. 6 tails.
Yeah, 6 tails. So I don't know how that came about. I know we've had. I saw the comet one. Can't remember which one it was now. Had 3 tails, didn't it? That was back in 1989 or something like that, or
I don't know.
Yeah, there was a comet that had 3 tails.
Right.
But in 1758, Messier was observing a comet when he was distracted by a fuzzy-looking object in the constellation of Taurus. On closer inspection, he realized that the object wasn't moving against the background stars, which meant it wasn't a comet. In an effort to prevent himself from mistaking the object of a comet again, Messier recorded its description and location, and thus began his catalogue of comet-like objects to avoid.
Right.
The comet-like object that Messier observed was a supernova remnant called the Crab Nebula. As the first object recorded in Messier's catalogue of nebular and star clusters, it is commonly referred to as Messier 1, or simply M1.
M1, yes.
M1. By the time of his death in 1817, Messier had added 103 deep sky objects to the catalogue, although many were discovered by other astronomers. The catalogue was revised in the 20th century and now contains 110 objects. As I said, his catalogue wasn't just his discoveries. In fact, the first 2, M1, was discovered in 1731 by an English astronomer, John Bevis.
Right.
And M2 was discovered in 1746 by an Italian, Giovanni Domenico Maraldi.
Right.
So the first actual discovery of Messier's, his own discovery, was M3, which was a globular cluster in Canis Venatici. in 1764.
And it wasn't just a catalogue of star cluster, was it either? Because he's got the Andromeda Galaxy in there and 31.
Yeah, exactly. I mean, I'll just give you a quick rundown of what's actually in it.
Yeah.
But I must point out that this is a catalogue for the Northern Hemisphere.
Sure.
There is one that is, there's probably several that can be seen from the Southern Hemisphere, depending upon your latitude. But there is one in the Northern latitude. If you're a higher latitude, it's hard to see because it very rarely pops above the horizon, so you can't image it. Because of course everybody likes to do a Messier marathon.
Yes.
When you try to catch all the images in one night, and that's usually sort of like around about February, March time.
Yeah.
And it's good fun. It's good fun. So to catch them all, unless you're in sort of like more towards the equator, a latitude towards the equator, you probably won't be able to catch them all. You'll be missing that one.
Yeah.
So the other way you can do it is robotic telescopes, of course.
Of course.
But the types of objects, excuse me, in the catalogue, there's 29 globular clusters, 28 open clusters, 26 spiral galaxies, 9 elliptical galaxies, 3 lenticular galaxies, 2 active galaxies, 6 emission nebulae, 1 reflection nebula, 4 planetary nebula, a star cloud, and 1 supernova remnant.
Right, which would be M1.
Exactly. But of course, if you notice the title is a catalogue of nebula and star clusters, as you said, Andy, he has got galaxies in there. But of course, at that day,
he didn't know there were galaxies. No,
they didn't know there were galaxies.
Absolutely.
They just looked like, and they thought everything was all in our own Milky Way. Galaxy, yeah, because ours was the supreme galaxy.
Yeah, absolutely.
He died at the age of 87, as I said, on 11th of April, 1817. But he did astronomy right to the very end. So he was, he stuck at it, and he took it. It was his passion, and he took it really well. Did it all the way to his grave. So that is Charles Messier.
Goodness me! Well, that's very interesting, Daz. That's another fine Messier you've got me into.
That's right. The only other thing I can tell you about the actual list, is the breakdown of the distribution across the constellations, if you would like it.
Go on then, that'd be interesting.
There are 15 objects in Sagittarius, 11 in Virgo, 8 in Comma Berenices, 7 in I always get this one, Ophiuchus,
right.
7 in Ursa Major, 5 in Canis Venatici, 5 in Leo, and 4 in Scorpius.
So Sagittarius has got the greatest concentration of Messier.
Exactly. And if I remember, we had that in a quiz not long ago.
We did. We had that in the quiz on Reach Out.
And I got it wrong.
Yeah, I did as well.
Yeah. So
I know now which constellation I've got to pay more attention to. And of course, where I live, it's quite high above the horizon. Whereas where you are, it's very low on the horizon. But
exactly.
Here I can see more or less a full constellation.
Yeah. So that's Mr. Charles Messier who gave us his, and it's a bit ironic that we don't associate Messier's name with his 13 comet discoveries, but with his catalogue of nebula and stars, the very objects he was trying to avoid. So yeah, it's a bit ironic that. But
I remember back in the 1980s, Daz, I was spent the night going through galaxies and star clusters with some friends. And I was eating a chocolate bar at the time, but it kept melting. I tell you what, I've never had a Messier marathon.
Oh, dear me. Oh, please don't do that again.
Sorry.
Yeah. See, is not for comedy for you. So
sorry about that, listeners.
That was Mr. Charles Messier for you.
it's very sad, in fact, that he's remembered for his catalogue more than for his comets.
Exactly. Yeah, exactly.
Considering
As you
that
said,
was
we don't
really
see
his
them come
life's
round.
work to search for comets. But on the other
Yeah.
hand, he has bequeathed to us a catalogue that all astronomers use. And,
Exactly.
when you're cutting your teeth in astronomy, that's your guide, basically, isn't it?
Exactly.
To deep sky objects. Yeah.
That's what I tell everybody. If they're starting out, and once they got past the step, once they've learned to star hop and all that, I say, if you want to go and buy a telescope, then that'll introduce you to deep sky objects. And the best way to start is go for the messier messier objects.
Yeah.
Because they're the easiest, and some of them are actually observable with the naked eye.
Yes,
if you're
indeed.
in dark sky places. So
M31, the Andromeda Galaxy, you can see with the naked eye. The Pleiades, of course, M45.
Yeah,
very clear, and many others. So there we are.
Exactly.
Okay, well, thank you for that. That's Charles Messier, author of the most famous catalogue in astronomy. I believe I'm right in saying that there are actually only 109 objects, not 110, because one of them's in there twice.
Yeah, that's it. There is a suspicion that one of them's been misidentified, and it's in there twice.
It's in there twice. Yeah, absolutely.
I couldn't tell you which one it was. I didn't.
I used to know that. I can't remember. Okay, then. Thank you for that. My turn now. C is for, believe it or not, Crab Nebula.
Oh, excellent.
But M1, here we are. Look at the link between that. We should be on TV with that sort of continuity.
Yeah. And it wasn't planned. It wasn't
planned. No. The Crab Nebula, I want to talk about the pulsar in the Crab Nebula. So really, C is for Crab Nebula pulsar. And it has a distinction. Now, you talked about this in your wonderful program about Dame Jocelyn Bell Burnell being the lady who made the first observations of the first pulsar, which was the Crab Nebula pulsar in M1. But that pulsar has another distinction, and I wonder whether you know what it is. There's something a little unusual about the Crab Nebula pulsar. Yes, it's a pulsar. Yes, it sweeps the sky with beams of radio energy that we detect from the Earth, and they are exactly the transmissions that Dame Jocelyn Bell Burnell detected. But
there is something I know strange about it, but I'm trying to rack my brain. I'm trying to think what it is. You'll have to enlighten me, Andy.
Okay, I'll put you out of my misery. Yeah. What it is, the Crab Nebula pulsar is one of just a few pulsars that are known to emit pulses of visible light as well as radio waves.
That was it, yeah.
Yeah, and if you, I'm sure it's on YouTube somewhere, but I've seen it. There's a video, which is an animation of the Crab Nebula pulsar actually flashing invisible light, not just radio light, invisible light. And I think there are fewer than 6 pulsars that we know of that actually emit visible light as well as radio waves. And nobody knows why this is. It's a bit strange. So, in other words, what the pulsar is doing, it's lighthouse-like beams of electromagnetic energy is sweeping the sky at longer or wider wavelengths than just the wavelength of radio waves. And why it should do that, scientists don't know. And it is very rare. It is very rare. And I think it's amazing that it was the first pulsar discovered that holds this distinction of being very, very unusual. It's not just your common, not just your run-of-the-mill common or garden pulsar. This is one that has something special about it, that it flashes in visible light as well as in radio light. So there we are. So that was it, basically. The Crab Nebula pulsar is an unusual one. And
because the Crab, the actual Crab Nebula, the supernova that which is it sits in Taurus, is about 11 light years across and sits about 6,500 light years away. And as you said, at the center there is the pulsar, but it was actually recorded by the Chinese astronomers in 1054 when it actually went
That's
off.
right. That's
And
right.
it did glow it actually was a daylight object as well that could actually
It
be
was.
seen because it was so bright. So yes, right, exactly. Yeah, so it's actually a nova that we actually know went off quite recently in
astronomical
galactic
terms.
times.
Yes.
So
Yes.
yeah.
It's
Oh, excellent. That's fantastic.
yeah.
And I also think, isn't there somewhere in America where there's an American native tribe? They live in the desert, and you go up into the rocks behind, and there's a cave, and I think the nebula's even depicted in the drawings that they've done in the cave, if I remember
Really?
rightly.
Well,
Yeah, I'd
it
have to
wouldn't
check on
surprise
that.
me because the Chinese weren't the only observers of the skies, obviously.
Exactly, yeah.
So,
So yeah,
but
thanks for that, Andy. Yeah, that's
that's
good.
okay. Right, back to you then, Daz. What have we got next?
I think I will go for C is for Cepheid variables.
Oh, interesting.
There we
Interesting.
go. What I'll do is I'll give you a brief breakdown of what they actually are, and if we need to go into a bit more detail, I can do. So Cepheid variable stars were named after the first of their kinds observed in Cephus. They are actually two classes of Cepheid. There is a type 1 Cepheid, which is basically called a classical Cepheid, and are a population 1 stars with high metallicities. So again, we come back to the high metal content in the actual star itself. We talked about that before.
Yes.
And a pulsation period generally less than 10 days. You've got type 2 Cepheid variable stars. They're also called W Virginis stars.
Right.
And are low metallicity. Population stars with pulsation periods between 10 and 100 days.
So they're much older stars, presumably.
Yeah, they're the older ones. That's right. Yeah, I nearly got that round the wrong way. Yeah. All Cephids are luminous yellow, and you'll find them in the horizontal branch of the instability strip on the Hertzsprung-Russell diagram.
Right.
And instabilities which cause their size and temperature to change give rise to the periodic variations in their luminosity. Now, it sounds a bit complicated. I'll come back to the Hertzsprung-Russell diagram in a second.
Sure.
In 1907, Harriet Leavitt discovered that Cepheid variable stars in the small Magellanic Cloud pulsated at a rate which depended solely on their absolute magnitude. This period luminosity relationship allows Cepheids to be used as standard candles once the pulsation period is known, to estimate distances to objects in which they are located. In fact, Cepheid variables formed the first non-direct method of distance determination and established the first rung of the distance ladder. All subsequent rungs of the ladder use Cepheid distancing as a stepping stone.
I see.
And of course, in the 1920s, Edwin Hubble, using variable stars to measure distances to nearby galaxies. Again, when he was looking, they were still considered to be nebula.
Yes.
At the time, it was thought that all the variables were type 1 Cepheids, but in reality, the sample also included what they call RR Lyra and VW Virginis. VW Virginis stars.
Yes.
It wasn't a Volkswagen.
No. The Volkswagen variable. That's a good name for a make of car, isn't it? The Volkswagen variable.
Yeah, exactly. And using this, Hubble also established that the universe was expanding, and also was expanding using spectroscopy and using the redshift. He was able to establish that the rate of expansion was faster than was getting faster, was actually speeding up.
Sure.
So that's basically what they are. I said I'll pop back to the Hertzsprung-Russell diagram.
Yeah.
Basically, it's a graph where you plot the stars, and it's basically the two axes are luminosity against
Temperature.
Their temperature. God, I struggled then. Luminosity against their temperature. And you plot the stars on there, because the stars' temperature can be estimated by their colors. And of course, the newer stars are blue stars. They're very bright, so they're very hot. Now, they appear at the top left-hand corner.
Yeah.
And then you've got what you call the main sequence that goes diagonally from the top left to the bottom right. And in all those stars, you've got all the stars that are burning. They're in they're called their main sequence, and they're burning hydrogen. Then what happens is, of course, as we all know, the bigger stars burn faster and brighter, so use up their hydrogen a lot faster, and then go into what we call a red giant stage. Now, on the diagram, this means they move from the main sequence up towards the top right into the red giant phase.
Yes.
Now, I mentioned in this little bit of a description that there is what is called a instability strip. Now, this is actually linked into the red giant stage, and the bigger stars will pass into the red giant stage and then come back out again as they basically pulse. This is what's causing the variability. As they pulse, their luminosity changes as well.
Right.
But Cepheid variables have a regular beat, and their luminosity can be predicted. And this is how we can use them as what we call a standard candle to gauge how far things are away.
That's right. I mean, this is looking at a distant car, because you know that all car headlights have the same brightness. Well, let's say for argument's sake they do, and I know some are brighter, but, or let's say all car headlights have the same brightness. So if you look at one at night, you can work out exactly how far away it is by how bright it appears, because you know how bright it actually is.
Yeah.
And this is what astronomers use to measure distances across the universe. In fact, the measurement of Cepheid variables, as Daz said, was what led Hubble to understand that, in fact, the galaxies are receding from us, or most galaxies are receding from us, except those gravitationally bound locally, like M31 that we mentioned earlier, and Andromeda. That's actually moving towards us because of the mutual gravity with the Milky Way.
That's right, it's part of the local group, yeah.
Yeah. But most other galaxies, whichever direction you're looking, are flying apart from us or moving away from us. And Hubble was able to ascertain the distances involved by using these standard candles to work out exactly how far the galaxies are away. So Cepheid variables are incredibly important in astronomy because, as Daz said, they do, or they can be used as so-called standard candles, because they can give you a standard distance to an object. That's very interesting, Daz. And,
do you know when the first, roughly, I'll give you sort of like, if you can give me the century, you can get a point of when the first variable, Cepheid variable, was actually discovered.
I believe that they were first actually observed by the ancient Egyptians.
Oh no, they possibly were. That's shot me in the foot, isn't it? But it was September the 10th, 1784. Edward Pigott first detected the variability of Eta Aquilae, which is a variable star.
Yes. And in fact, then, just out of interest, that was the year after the Messier catalogue was published.
Oh, okay, then that's fantastic.
Because that was published in 1783. There we are, another link.
Yeah. And as we said about the Cepheid variables, and of course it wasn't until 1908 that we found out how. So it was a good 200 odd years, nigh on 200 odd years, that we actually were able to find they were a useful tool, because it was 1908 when Harriet Swan-Leavitt basically made the link between their pulsations and their variable brightness and all that. But of course, when in 1924 Edwin Hubble established that the well, basically, the first thing it told us is that because he used Andromeda, he was looking at Cepheid variables,
Yes.
as I said, in Andromeda. Well, of course, the first thing it told him, and using the distance, that Andromeda, the stars in Andromeda, was outside the Milky Way. So that first told us that the the Andromeda was a galaxy in its own right.
Yes,
So
that's
that
right.
was the first time that we suddenly realized, well, hang about, we're not, we're not the only galaxy. These are other galaxies.
Yes.
But of course, then he also established that the inflation was happening, and also that it was speeding up from the same information. And of course, this all kicked off because you had your deniers. We talked about Mr. What was his name? I'll forget that anyway. But it started off the debate. The people who believed in the static state debate. It was basically this debate was called the Great Debate.
Yes.
And you had the people who believed in a static state, that everything was as it is now and it always will be. And then you had the people who basically, because two of those was Fred Hoyle and Einstein. Even they were both in that camp.
They were indeed. Sorry, Daz. When we talk about acceleration, I think it's only fair to point out that Hubble was the person who discovered that the further a galaxy is away from us, the faster it's moving.
Yeah.
And this became known as, in fact, Hubble's law, believe it or not. That the further a galaxy is from us, the faster it's moving. Yeah. This is not to do with the acceleration of the universe, which we now call dark energy, which was discovered in the late 1990s. So it was actually Hubble's law that Hubble discovered. Coincidence, that, isn't it?
Exactly. Yeah, that is really strange. So like I said, in the great debate, you had two sides of the camp, and Fred Hoyle, even to his deathbed, still maintained that everything was still static. He was like a dog with a bone, wouldn't let it.
But he never ever had an explanation for what the cosmic microwave background could be, apart from being what it is, of course.
Exactly.
So he was an irascible old person, but one of the greatest scientists who ever lived, in my opinion.
Yeah. So that was C for Cepheid variables, and
C for Cepheid variables, a very, very useful tool in astronomy for measuring distances. Yeah, absolutely. Thank you for that, Daz. Right, back to me. C is for comet. Now, not any comet. There's another link. We've been discussing comets with Messier. This is no ordinary comet. This is comet 2014 UN 271. Don't know whether that rings any bells with you, Daz.
It rolls off the tongue there, doesn't it?
This is an object from the Oort cloud. So, in other words, a long period comet that has just entered the solar system is estimated to be between 100 and 370 kilometers across. So it's a huge object. In fact, it's the biggest object that we've ever seen enter the solar system from the Oort cloud. Now, the bad news is, if you're getting excited about this forming a brilliant comet in the night sky, it ain't going to, because its orbit means that it's only going to penetrate the solar system as far as Saturn, and then it will move out again. However, astronomers are saying when it does get to Saturn, it could be a bright comet in terms of comets, but it's unlikely to get brighter than Pluto in the night sky. So unfortunately, we're not going to see this as a spectacular comet. Now, its orbital period is estimated at anything between 400,000 years and 1.5 million years. Scientists hope to get a better fix on that as it approaches its perihelion, which is the closest point to the sun. And it's going to reach its perihelion just about at the orbit of Saturn in the year 2031, so another 10 years, and it will be at perihelion. But as I say, this is an object that isn't very strongly bound to our sun. Otherwise, it would be penetrating further into the solar system. It's only going to get as far as Saturn and then move out again. And we'll certainly never see it again in our lifetime, nor many lifetimes. But it is the biggest object ever to enter the solar system, biggest known object ever to enter the solar system from the Oort cloud. Now, in case any of our listeners don't know, the solar system is surrounded by a shell of perhaps trillions of icy objects, which are the leftovers from the formation of the solar system. And this is known as the Oort cloud, after Jan Oort, the astronomer who postulated its existence. It's reckoned to start out well beyond the Kuiper belt, which is really the third zone of the solar system, and one that we've only become aware of since really the beginning of the 90s. And it penetrates maybe out as far, it extends out as far as maybe 1.5 light years from the solar system. The answer is we don't know. We actually don't have any definitive proof that the Oort cloud exists at all. But there must be a reservoir of comets outside the solar system. Otherwise, where do all these long period comets come from? And by long period, we mean comets that take, thousands or even millions of years to come into the solar system and disappear out again. And what normally happens, or what is thought to have happened with several times with the Oort cloud, where we've seen these long period comets, is that something has given it a bit of a gravitational nudge in the Oort cloud. Imagine this spectacular cloud of icy objects, which then fall into the solar system as a result. As they approach the sun, the material starts to sublimate, that is, turn directly from a solid to a gas with no liquid stage in between, and shoot out behind them a long tail of material, which is the stuff that is sublimated off the surface, boiled off the surface, if you like. And this is what a comet is, and this is why a comet's tail always faces away from the sun, because the sun's radiation is streaming the material out behind the comet, and some of those tails can extend for millions of miles. And that tail always points away from the sun. And a lot of comets also have a secondary tail, which is known as the ion tail, which is a trail of charged particles, thanks to the sun radiation, which usually shoots out at an angle from the comet. And it's usually blue because it's ionized material from the surface of the comet. It has a charge, in other words. So there we are. Anyway, getting off the point a bit, but Comet 2014 UN271 is the largest object ever seen to enter the solar system from the Oort cloud. It's going to get as far as Saturn in 2031 and then go on back out to the Oort cloud. And perhaps it will take between 400,000 and 1 million years to complete one cycle, one orbit through the solar system. So there you are, Daz. Interesting, eh?
Yeah, that's interesting. Because I actually have read about this, and I've actually downloaded it today. Right. But I haven't had a chance to read it. And that's because I was a bit confused when you said it's 2014, because usually the designation of that is when it is actually discovered.
It was first observed in 2014. Yeah,
exactly. And it was dubbed as 2014 UN 271. The object is likely to make a close pass by the sun, bringing it into Saturn's orbit in 2031, as you said.
Yes.
The object was first was observed in data from the Dark Energy Survey. So that's how right. It was. And which was conducted between 2000 and 2018. So that explains, yeah. And as you said, what was the orbit you said? Because I've got here 6. What's that supposed to be?
Well, I have read several different estimates of its orbital period. Yeah. One I read said 3.5 million years. Another one said between 400,000 and 1 million years, which seems more like it to me. And there may be others, but they don't really know, and they won't know till it gets a bit closer that they can.
That might be a bit dimmy, because what I'm actually reading here, it says it has an orbit of 6, 0. Is that supposed to be 600,000 years or? I don't know
Could
what
be.
if they've got their commas in the wrong place. I think they've missed something out.
Right.
That doesn't make sense. Yeah, it's very interesting because it's something to watch, especially if we're still around,
Yep.
God willing, that we actually get to see it, and if it becomes a object of that we can actually observe, it would be very interesting.
But it's not going to. Apparently, they say it's not going to get brighter than Pluto. So you'll need a large telescope to see it. So.
Yeah, exactly. So yeah,
sorry about that. That's not going to be a great comet.
I don't know whether it's hype here. They're talking about that. They reckon it's a dwarf planet. From the
it's not big enough to be a.
Yeah, so really I think that's just, as we know, is all the hype that they want to
hype on the internet. I don't believe it.
No, in the news.
I've never seen that ever. Right, Daz. So back to you. C is for.
Oh, hang on, I'm not ready yet. Okay. Right, what we'll do, I will do now, is what we were talking about, the cosmic microwave background.
Oh, C is for cosmic microwave background, right?
Yes. The CMB, as it's called, the cosmic microwave background. The cosmic microwave background is basically part of the evidence towards the Big Bang theory, that has how the universe started. It's basically, how can I best describe it? It's how can I say it? It's like a fog bank.
Mm-hmm.
When the universe started, there was a big primordial soup of gases and energy, high temperatures, which basically everything was so energetic due to the heat and the radiation that was being produced that nothing could form. And basically we had what we called the inflation, which is why the Big Bang is sometimes considered to be a misnomer. There wasn't actually a big explosion, but what we had to wait for this big fog of or soup of high energetic particles to cool down so they could start the actual in the quantum world, these atoms and all that could start to form. Yeah. All these particles could start joining together, because until the temperature reduced, all these things, if they appeared, were instantly absorbed again by something else.
That's right.
And of course, this was basically a very thick soup that no light, no photons could escape from. And it wasn't until this massive fog had cooled down sufficiently that photons would actually have the chance to escape.
Yeah.
And once they were able to escape, that's when we had our first light. So the cosmic microwave background, it gives us a rough age of it gives us our limits of the viewing that we can actually see, which is about 13.8 billion years.
Yeah, that's right. Because people often ask, don't they? If we can look far back in times with telescopes, why can't we go back and why can't we actually see the Big Bang? And this is right. The answer is you'll never get closer than 380,000 years after the Big Bang because it's just fog.
Exactly. Yeah, exactly. You're spot on there, Andy, because this, like I said, this was a massive fog. It was opaque. You couldn't see. If you were stood in it, well, you wouldn't be stood there long. If you were there, you wouldn't be able to see your hand in front of your face, because like I said, it was so opaque. It's like the old smogs of London town.
Yes.
And once we got to the coolness that the first light could escape, that's where we can see back to. The microwave background now is its temperature is about where it was sort of like something like 3,000 degrees Kelvin. Then it is now cooled down to, they reckon it's about 3 degrees Kelvin. Just below
not far above absolute zero.
Yeah, not far above absolute zero. And of course, as we know, that is very cold. Was it 274?
-200, yeah, something like that.
Yeah, minus 274 degrees centigrade. It uses the same scale as the centigrade, but absolute zero is way below. Is 274 degrees, minus 274 degrees. So you're still very, very. Although we can detect it, the only way we can detect it is in X-ray.
And wasn't it
a microwave? Sorry, a microwave.
Yeah,
That's
microwave.
Right.
Because the expansion of the universe has stretched the waves out so much that it's moved
exactly
through radio into microwaves. And its temperature was actually very closely predicted by Big Bang Theory. I cannot remember which scientist it was who made the final prediction, but this is one of the cornerstones of Big Bang Theory. The Big Bang Theory said, if the Big Bang is right, there should be a wave of radiation traveling through the universe at just a couple of degrees above absolute zero, at microwave wavelengths, and we should be able to observe it. And lo and behold, that was exactly what was discovered. The famous story about pigeon dung.
Exactly. That's what I was just going to come to.
Tell us a story about pigeon dung, Baz.
Well, what it was is the microwave background was first predicted in 1948 by Ralph Alpher and Robert Herman.
Yes.
And they predicted that it should be about 5 degrees K, if I remember it rightly. What it was is that these chaps, using what was called the Holmdel horn antenna, which looks like a big hearing horn that somebody used to hold in olden days, before we had hearing aids and all that, electronic hearing aids. They were going to use it originally for satellite communication, and
that's right. It was owned by Bell Labs, wasn't it?
That's right, by Bell Labs.
Yeah.
But what they found is that when they got hold of it, wherever they pointed it in the sky, they had an annoying hiss. So what they did is they got inside this telescope, because this horn, if you call it a telescope, it's a hearing device. Basically, it's collecting all the noise and all that from to detect all the radio waves and things like that. And they totally cleaned it out, and they found inside that it was absolutely covered in pigeon poo. So they cleared all that out, but still the hiss persisted. And they did have some resident pigeons actually nesting inside the horn itself.
They did. They got rid of those, though.
They got rid of those. It's debatable whether or not they euthanized them or whether or not they caught them and took them away, and they live very happily on a desert island somewhere. But it did cause a bit of a kerfuffle at the time.
You're a bit of an old romantic, aren't you, Daz?
Oh, yeah. Yeah, so...
pigeons living on a desert island. What an image.
Yeah,
drinking
pina coladas.
Their sunset years. Yes,
exactly.
Pina coladas. How lovely.
Pina coladas and stuff like that. But of course, in the end, they couldn't get rid of this incessant hiss. And basically they were talking to some of their colleagues and all that, and they were talking about then they were put on to some other astronomers who were actually searching for the cosmic microwave background.
Right.
And once they got in touch with them, it suddenly clicked into place that what they were listening to was the oldest heat in the universe. It was the cosmic microwave background. And so between them, Princeton and Bell Labs and Mr. Alpha and Mr. Herman, they were able to predict, to decipher that this was the oldest heat in the universe, and it came from the Big Bang. And they were able to work out that it was the temperature was about 3 degrees Kelvin, and it was about 13.8 billion years old. Amazing. So that's how they discovered it. but it's still kicked off the old debate.
Yes,
because it basically confirmed the Big Bang. And
well,
of
it
course,
was the final nail in the coffin of steady state
exactly,
theory, wasn't it? Because
exactly.
the proponents of steady state theory literally had no explanation for the cosmic microwave background.
They tried to say it was scattered light from distant galaxies.
Well, they would, wouldn't they?
Yeah, they weren't going to go down without a fight.
They were never going to admit they were wrong, were they?
No, not the likes of Fred Hoyle. Or,
no.
I mean, Einstein did come around to the theory, but because he had to put into his famous equation of general relativity, he had to put what was it called, Andy?
A fudge factor, the cosmological constant.
Yeah, that's right, cosmological constant. But as it appears now with dark matter and dark energy, and things like that, it appears that this could be on the right lines.
Well, that's right. In fact, dark energy has many of the properties that Einstein ascribed to his cosmological constant, which was a fudge factor, a mathematical fudge factor that he introduced to stop the universe expanding because he didn't believe in an expanding universe.
Exactly. Yeah.
So he came up with this lovely mathematical trick that would basically counteract gravity and stop the universe expanding. And we now observe dark energy, which has the effect of expanding the universe, but even faster. It's making the expansion of the universe accelerate. But it has many of the characteristics of Einstein's cosmological constant.
Exactly.
Yeah, and I had this theory that if we ever find out that dark energy is very much akin to Einstein's cosmological constant, and that it may have been a mathematical trick that it came up with. It wasn't a very scientific way of doing it, because in science, you should never follow what you believe. You should only follow the observations and what the evidence shows. But I have a theory that if anybody ever does work out what dark energy is, there'll be a puff of smoke and Einstein will appear and he'll just say, "I told you," and they'll disappear again forever. So, so there we are.
With a big grin on his face.
Right. The other thing about the cosmic microwave background, in the days when we had the old CRT TVs, in between channels, you got snow on the screen. And 1% of that snow that you see and 1% of the hiss that you hear when you were between channels is the dying echo of the Big Bang. So you could actually watch and listen to the Big Bang, or at least 1% of it that you saw was the Big Bang, which is a crazy thought. It's a shame we don't have those TVs anymore, because I used to
That's right. You were actually seeing the oldest
light in the universe.
That's exactly
amazing. Truly
amazing. So that is C for the cosmic microwave background. I hope you understand that.
Well, thank you very much, Dazza. That was very nice. Okay, C is for Calypso. Ring a bell?
That was close.
Calypso is a moon of Saturn. Now, it's got a mean radius of about 6.5 miles. It's got several craters. It's got a young surface. But the thing that it has is one of the brightest albedos in the solar system. It's one of the brightest objects in terms of the percentage of sunlight that it reflects in the solar system. And nobody understood why until Cassini started examining Saturn's other moon, famous moon, Enceladus. And what Cassini, which orbited Saturn between 2004 and 2017, what Cassini found was that Enceladus is sending vast geysers of ice and water vapor from cracks at its south pole, which are nicknamed the Tiger Stripes because of their appearance, out into space. And this material actually forms one of the rings of Saturn, the E ring. And Calypso, as a moon, does not orbit far from the E ring. And scientists now are pretty sure that the reason that the surface of Calypso is so bright is that it's literally being sandblasted by the material gushing out of Enceladus and constantly remodeling its surface, scraping everything off, and this is why it's so bright. And if you look at pictures that Cassini took of Calypso, it didn't get that close to it, but you can see that it's a very bright object indeed, thanks to the sandblasting, if you like, that it's receiving from the material gushing out of Enceladus in those famous geysers, if you like, want to call them that, from the south pole of Enceladus, which has told us that Enceladus has a subsurface warm, salty ocean beneath its icy crust. So there you are. That's Calypso, sand-blasted moon of Saturn.
With the highest albedo.
One of them, not the highest, but it's got one of the.
One of the, because we spoke about that when we did A.
Yes, we spoke
and
about
you did ask me a question which I forgot to get back to you on. What was the albedo of Venus, because it's covered in clouds? And all that.
Yes, I do remember.
Well, that is actually the albedo rating is 0.76, and as we recall, that means 76% of the light.
So that's reflected. 3/4 of all the sunlight hitting Venus.
Exactly. Yeah.
Wow.
So
that's right. I was looking at it last night, funnily enough.
So it was that was an interesting fact. And as you said, the most visual albedo is Enceladus itself.
Yes, it is.
Which is 0.8, which is 80%, I presume. Yeah, so it'll be 80%.
Well, yeah, that's right, because the surface of Enceladus is pure white ice.
Exactly. So, yeah, that's an interesting fact, because I've actually, like you said, I thought you'd have a list, and well, I've got a list now. In fact, I've got a table. So I've got a table. So yeah, I just thought you'd like to know that as you asked, it's 76% of the light from that hits Venus is reflected back. So that's why we see it so bright in the sky. So just an added little factoid for you there.
Oh, that's amazing. But Calypso's albedo, I don't have the figure to hand, but it's certainly very bright.
Very bright, yeah.
Very bright indeed. So there we are.
Excellent.
And that's Calypso for you. Over to you then, Daz.
You'll see the reason for the sharp intake of breath when you said Calypso, because I've got Callisto.
Oh, you've got Callisto, the other moon of Saturn, right?
Yeah, C is for Callisto. It's Jupiter, isn't it?
Sorry, Jupiter. What am I talking about? Yes,
yeah,
Jupiter.
Yeah.
The Galileo moon.
You threw me there. I thought
I threw myself.
Yeah, so it's a moon of Jupiter, and like Ganymede, mostly ice, but containing lots of rock. So it's basically a dirty snowball.
Right.
It's heavily cratered, showing its surface to be very ancient. Callisto was imaged by the Voyager originally. It showed a vast impact site. Now, I say an impact site, not a crater, on Callisto, which is 4,000 kilometers in diameter.
Wow.
Making it the biggest known impact structure in the solar system.
Really?
And it's called Valhalla.
Of course it is.
Yeah. Still can't work out the link between Valhalla and a massive crater, not crater, a structure like that. Yeah, it is very subtle. When you look at it, it's just you can see the shock waves where they've all formed rings around the central point, but they're very subtle. They're very low. They're rounded. There's nothing jagged or anything about them. But as I said, they stretch over 4,000 kilometers.
Right.
And it said, yes, it is very subtle. That each of the numerous visible shock wave rings, escarpments, rise only about 1 to 2 kilometers above its surroundings. The impact forming Valhalla must have taken place at a time when Callisto's lithosphere, now that's the hard crust that's on the outer side, was thin, and its astrothene sphere was warm, and the astrothenos sphere, was warm and was still malleable enough to smooth out the surface topography when this thing hit. So basically, it probably did form a big crater, but because everything was malleable and subtle, and we're talking about an ice mixture and all that, it actually smoothed it all out. So, like I say, you just see this very big round structure.
Yeah.
And at the center, there's a bright area, and it's about 300 kilometers across. The site of the now vanished transient cavity, so where it actually hit.
Right.
That was the impact area, and the reason it's basically disappeared is that the ice actually came the molten, because of course heat would have been created when it was hit.
Sure.
It melted the ice and it filled the actual central crater.
Right.
What else have we got about it?
This was all presumably a very, very long time ago.
Exactly, because like I said, the surface is very, very ancient. It says this means due to Callisto being mainly an ice rock makeup, it could not support the weight of the higher or high shockwave rings.
Right.
So they basically sank down and smoothed themselves out. And as I said, the central crater was filled with ice.
Wow.
Callisto is also thought to have an internal salty ocean, and this is inferred from its induced magnetic field. It's actually got a magnetic field.
Right.
Although this doesn't seem to have any discernible effect on the surface.
So in fact, all 4 of the Galilean moons around Jupiter, and we call them Galileo moons because they were first seen by Galileo. His telescope was not powerful enough to see any fainter moons. Just the 4 inner brighter moons of Jupiter. All 4 of them are suspected of having underground oceans.
Yes,
but in the case of Io, it's not an underground ocean of water; it's an underground ocean of magma. Because Io is constantly squeezed and stretched by Jupiter's immense gravity, meaning it's the most volcanic world in the solar system, and in fact the first world outside the Earth where we saw active volcanoes. And the first of those was discovered by a junior NASA navigation engineer called Linda Morabito in the late 70s. She was calibrating the guidance system for Voyager and happened to discover this sort of bump rising off the surface of Io that she thought was another moon behind it, but it turned out to be an active volcano. Anyway, sorry, getting off the subject.
Yeah,
but
no, because Io's that lovely sort of like pizza looking.
Oh, it's a beautiful moon, absolutely
beautiful. A tormented world, but really nice to see.
Well, they're reckoned to be anywhere between 100 and 150 volcanoes erupting on Io at any one time.
Yeah. So of course, Io is a typical volcanic planet as we know it.
Yes.
But as you said, the others are all, their volcanism is cryovolcanism. So
yes, that's right. So we've got 3 lovely moons with underground oceans to investigate.
Yeah, and the sooner we can get there, the better, as far as I'm concerned. Because I think
great. Well, that's Callisto then.
Promising. That was C for Callisto.
Oh, thank you, Daz. C is for Cordelia. Does that one ring a bell?
Another one.
Another one.
Cordelia. Isn't it? You'll have to remind me which planet it.
It's a moon of Uranus.
Uranus. That's right. Yeah.
It is in fact the innermost moon of Uranus, the one closest to the planet. It's got a size, an estimated 50 by 50 by 36 kilometers. But it's remarkable for another reason. It's one of the 2 shepherd moons of Uranus's rings. Now, we didn't know that Uranus had rings until Voyager got there in 1986 and detected this faint, but nonetheless still there, ring around Uranus. And this is different from Saturn's rings because the rings around Saturn are mostly ice. The ring around Uranus is mostly dust. So it's very dark. So this is why we didn't see it until we had a spacecraft literally sitting there right on top of it in the form of Voyager. So it's the innermost moon of Uranus. It's one of the shepherd moons. Now, this means that the moon keeps the ring of Uranus in place as a ring by its gravitational interaction with the ring. It maintains the ring, stops it from falling inwards into the planet. And of course, you also need one on the other side of the ring to stop the rings dissipating outwards into space. And you don't know the name of the outer shepherd moon of Uranus, do you, Daz? Just out of interest.
Not offhand, not offhand.
No, it's Ophelia.
Ophelia, that's right.
Ophelia is both Shakespearean characters from King Lear, and they are the shepherd moons. They keep the ring in place as a ring, without which it would dissipate. Some of it would fall inwards onto the planet, and the rest would fly off into space. Now, interestingly, before these were discovered, Cordelia and Ophelia, or at least what their function was known, there was great skepticism among astronomers that shepherd moons actually existed, that there could be moons which maintain planetary rings. And when Uranus's ring was discovered, and then Cordelia on the inside and Ophelia on the outside of the ring were definitely shown to be keeping the ring in its shape and configuration. And that was when astronomers finally realized, yes, there are such things as these so-called shepherd moons, which keep planetary rings in place by their gravitational interactions with them. So that's why Cordelia is quite interesting, because it's not only the innermost moon of Uranus, it's the inner shepherd moon for Uranus's ring system. So there you are. That's interesting, isn't it?
That is very interesting. And what I'd like to do is quickly move on, because time's coming up against us.
Right.
Is to another moon.
Another
Sharon.
moon. Great.
Yeah, Sharon.
Yeah. I thought of using Sharon, but I thought no.
Yeah, it was discovered by an American, James Christie, and it was discovered in 1978. Now, when it was first, it can't be seen individually. It just looks like a bump.
But we'd better say first of all that it's a moon of Pluto.
Oh, moon of Pluto. Oh, I do apologize. Yeah,
that's okay. Just to clarify.
And it's yeah. So basically, one of these moons, Pluto and Charon, are, as with Earth, the moon slows the Earth down, and also the Earth slows the moon down.
Yeah.
And it's slowed the moon down sufficiently now that we always have the the moon is tidally locked, which means the same side is showing to us all the time.
Yes.
Well, Pluto and Charon are a rare example of where their sizes are quite similar, and they've both tidally locked each other. So the surface facing Charon is always the same surface that Charon will see, and vice versa. Pluto will always see the same side of Charon. They're in this sequence where they're literally together all the time. So that is so basically. I'm assuming there's no tide, so there'll be no surfing on Pluto. Or should I presume them?
No.
So Christie would have liked to have called it Charlene, which was his wife's name.
Charlene. Sorry, that was Marlene. Marlene.
Yeah.
Marlene.
It's all right. I do exactly the same. But her name was shortened to Char. So he proposed Charon, which the International Astronomical Union accepted, because, of course, all the names have to go through the
IAU.
IAU.
Yeah.
And of course, Charon, as you said, you were just talking about the names of other moons around planets. They always try to follow a theme.
Yes.
And of course, Pluto was the ruler in Greek mythology, the ruler of the underworld.
Yes.
And Charon is the ferryman that conveys the souls of the dead across the river Styx to Hades.
Yes.
So it's basically Greek mythology, and it's to do with the underworld. It has Pluto has 4 other moons, and there's Nyx, which is the goddess of darkness and night and mother of Charon, the ferryman. There's Hydra, the 9-headed serpent, and this is possibly a recognition of for the short time that Pluto was considered the 9th planet. So you've got the 9-headed serpent, and then you got Styx, which is the goddess of the river Charon, which is crossed, as I said. And then you've got Cerberus, which is the 3-headed dog that guards the entrance to
yes, indeed, Cerberus.
To the underworld.
Yes.
They did have a load of other names ready for when New Horizons flew past in July 2015, but it didn't find any. And of course, with Pluto and Charon, their rotation point, their barycenter of point of rotation is outside Pluto. So in effect, they orbit each other.
Right.
And they think Charon was created by a giant impact, the same as the moon was. So, and the only other thing I will say on this is that when New Horizons flashed past, it was actually carrying the ashes of Clyde Tombaugh, who discovered Pluto in 1930.
Yes, indeed.
Yes,
there we are.
So,
Charon is an incredible. I mean, the Charon-Pluto system is often called a double planet. Well, to be more exact, it should be called a double dwarf planet now, of course.
Yeah, exactly.
Now that we've realized our mistake and designated Pluto correctly as a dwarf planet instead of a planet, which it never really was. There's something interesting about the North Pole of Charon, and that is that it's red.
Yeah.
And this is thought to be the effects of tholins, which are ethane and methane. When you subject them to sunlight, they form this sort of red goo, and dropping from Pluto onto the North Pole of Charon. There you go.
Yeah, we saw that with New Horizons, and it was one of the shocks.
And it was very bright red, wasn't it?
Exactly.
Very noticeable. Very noticeable. Yeah.
Thanks for that. Yeah, that was good. That's
great. No, thank you. Well, listeners, I'm afraid that's the end of another edition of the amazing astronomical alphabet. So Daz and I will say goodbye until next week. If you'd like to write to us at any time, give us some feedback about the program. Tell us what you like, what you don't like, what you'd like to see, etc. We'd love to hear from you. You can email me. I'm andy@astroradio.earth. We'll be back next week with the amazing astronomical alphabet. And next week we'll be doing the letter D. So until next week, have a fantastic week. Look after yourselves, and we'll see you next week, won't we, Daz?
Yeah, we certainly were. It's been a great fun again. It's surprising how quickly the time goes.
Yeah.
And I look forward to the Ds.
Me too.